Hello everyone. In my last video I have explained about the ray diagrams or the images formed by the convex lenses and the distinguish between the real and the virtual image. Our today's topic is the images formed by the convex lenses and some important formulas which we are using in our numericals. So here today I have taken first image formed by the convex lens. See here everybody can see this is a concave lens, right? See, there are two cases only when the object is kept at infinity or either in between the infinity and the optical center. Two only cases are there. The first I have taken here, see, the object is just placed anywhere in between the optical center and infinity. Here it is the object. See, when the incident ray just strike the concave lens, because being the concave lens is a diverging lens, the ray which will be diverge, right, it goes away, and the second ray always passes through the optical center like this, right? So it doesn't changes its path. So here they are not going to meet at any point, so we are just extending in them in backward directions. So here they are going to meet. See here, this is the image. So this image, what does this image say? This is smaller than that of object. It is in between the infinity and the optical center, and the nature of the image is virtual and erect. Generally all the images which we are getting by the convex lenses are virtual and erect. Erect means it is just in the same direction wherever the object is just placed. See here I have made a table. See, there are two cases. At infinity, when you will keep the object at infinity, you will get the image on the f1. F1 means on the same side of where the object is placed, and the size of the image will be point sized image, means very small, or you can say diminished. Or the nature of the images, I told you, it will be virtual and erect. Virtual means which we cannot store for the longer time, right? And the between optical center and infinity, the same way we will get the image also between optical center and infinity. The size of the image will be smaller as compared to the object, and the nature will be virtual and erect. Now we are moving to the Cartesian sign conventions. The Cartesian sign conventions rules are very important for doing the numericals. Means this is just telling us where we have to take the distance is positive and where we have to take the distance is negative. See here, when the incident ray is just moving in this direction, this is for convex lens, right? This is the optical center, right? So if the incident ray is just moving in this direction, everybody knows number line. As number line, we are taking left side negative and right side positive. In the same way you can learn it. The distances which is just left to the lens, it is negative, and which is to the right, it is positive. Clear? Then all the distances we are just counting from the optical center, measured from the optical center, right? And the height of the object or height of the image will be calculated. Above the principal axis will be taken as positive, and below the principal axis will be taken as negative. This is sign conventions. This is new sign conventions rules which we have to follow for the numericals. When we do the numericals, that you'll understand more. See, this is same for the concave lens also. If the direction of the incident ray is just towards the right hand side, then the distance of the object will be taken as negative to the left, and to the right it will be taken as positive. The height above the principal axis will be taken as positive, and below it will be taken as negative. This is the sign convention. Now we are moving to the lens formula. See, what is lens formula? This is lens formula, that is 1 upon f is equals to 1 upon v minus 1 upon u, right? This is f is equals to focal length of the lens, v is the distance of the image, and u is the distance of the object from the optical center. It is compulsory. Clear? This is written here, f is focal length, v is distance of image from optical center, and u is distance of object from the optical center. Now what is the power of the lens? See, the capacity of lens to converge or diverge incident ray is called as power of the lens. Power, capacity, we have learnt it, means how much it can diverge or converge. This is called power. Generally, in the normal terms, power is just inverse of the focal length. The inverse of the focal length means P is equals to 1 upon F, where focal length is given in meter, right? The unit of the power of the lens is diopter. 1 diopter is equals to 1 upon 1 meter, right? This is called 1 meter. When the focal length is 1 meter, then the unit of the power of lens will be 1 diopter. The diopter can be written as like capital D. Now magnification. Everybody has heard the word magnification. Means how much magnified image, how much bigger, smaller you are getting. What is magnification? The ratio of the height of image to the height of object. This is ratio, means how much size of the object was there and how much image you are getting it. That is M is equals to H2 upon H1. This is height of image H2 and H1 is height of object. M is equals to, again in the second definition, it is distance of image upon distance of object. That is V upon U or I upon O. I means image, O means object. Clear? Now next is, what is combination of lenses? The combination of lenses means when two lenses are combined together. When two lenses are combined together. If lenses with the focal length of f1 and f2 are combined together, then the effective focal length will be given by f. That is calculated with the formula 1 upon f is equals to 1 upon f1 plus 1 upon f2. Either have you done that before? So this is just mathematical expression when you have to find out the effective focal length will be the product f1 upon f1 into f2 upon f1 plus f2. Right? This you can use in numericals. Just an important note, when these lenses are combined, what will be the power of the lens? If P1 is the power of one lens and P2 is another one, then the two lenses with P1 and P2 are kept touching each other, then the power of the lenses will be sum of individual power of lenses. This is called algebraic sum of individual power of the lenses. Now we are doing one numerical so that you can understand all this properly. See here, this is a question. An object is placed vertically at a distance of 20 centimeter from the convex lens. Then if height of object is 5 centimeter and the focal length of the lens is 10 centimeter, what will be the position, size and nature of image? How much bigger will be image? Means magnification you have to find B as compared to the object. See H1. See H1 is 5. It is given in the question. F is 10 focal length of the lens. U is minus 20. You have to find distance of image, height of image and magnification. So by using lens formula, 1 upon V is equal minus 1 upon U is equals to 1 upon F. Now 1 upon V is equals to 1 upon F plus 1 upon U. We have taken it to the right hand side. Now see 1 upon V is equals to 1 upon 10 plus 1 upon minus 20. Here we have taken minus 20 as the distance of the object U is taken as negative by sign conventions rules. Now LCM 20. Now 10 2s are 2 plus minus 1 1 upon 20. By comparing this V is equals to 20. Right? This is called distance of image from the optical center. It is 20 centimeter. Now you can see magnification. M is equals to H2 upon H1. That is V upon U, or cross multiplying H2 you have to find out. We have V, we have U, we have H1. So V is 20, U is minus 20 and H1 is 5. Right? So H2 is minus 5 centimeter. That H2 is minus 5 centimeter means the image will be below the principal axis. Right? Now magnification. The magnification will be V upon U. That is 20 upon minus 20, which is minus 1. And the power of the lens will be 1 upon F. That is 1 upon 10. And 1 upon 10 centimeter. You will convert it into meter. It will be 0.1, which is equals to 10 diopter. So I think everybody has understood how we have to do the numericals. In the next video, I will tell you about the human eye Thank you so much.